Let's go. Starting. Yep. Okay. So, Doppler effect and atomic spectra. And we'll review Doppler again. Now, those are your key learning intentions. We talked about this before. We've talked about how Doppler shift tells us that galaxies are moving away from us. Okay, but the Doppler shift of what? Of light. And how is that measured? And that's where atomic spectra comes in. Okay? And what we'll have a look at, there's that Doppler effect horn again, one more time. Always good value. And that, so you've got that high frequency, high energy to low frequency, low energy as it comes down. Now in terms of, oops, I'll just jump to the next slide. And that's the slideshow we've seen before. So in your Doppler effect slideshow, you've already got those notes there. Okay, the Doppler effect is the increase or decrease in the frequency of sound, light, or any of these EM waves. And we've talked about this image before. From the point of view of the observer here, when the car is approaching, are the waves compressed or are they lengthened? Compressed. They're compressed. So is it blue shifted or red shifted as you get that approach? Yeah, that's the blue shift there. The blue shift, if you remember the little rocket ship, if the observer's eye is here, the rocket appears blue as it approaches. The blue shift means that as they move together, the waves are shortened towards the blue end of the spectrum. As the car moves away, you get the stretching of the waves. They're lengthened out to the red end of the spectrum. Now in terms of Doppler, what people have observed, or astronomers have observed, is that galaxies, whichever direction you look in, other galaxies other than the Milky Way are redshifting away from us. Okay? And that's why that is significant. That was the key, or one of the key pieces of evidence that demonstrated that the universe is expanding and that the steady state theory could not be correct, because the universe wasn't unchanging, everything was getting further and further apart. So, that was the significance of redshift. There's another way of describing it. The train horn, the waves being compressed, the high pitch of the train horn as it approaches, the low pitch of the train horn out as it goes. Yeah? Right. This is where it becomes more complex. Atomic spectra. This is the graph that shows us that in terms of Hubble's law, the further galaxies are away, the faster those galaxies are travelling. We talked about that last class as well. So that as I said, when you look at a graph, it's easy to look at 50 points or 100 points and get confused and say, I'm not quite sure what that's showing me. So just pick one. That point right there, pretty far distance, pretty high speed. That point right there, not too far away, low speed. So that tends to show me what the graph is talking about. That the greater the distance, because this is the independent variable and this is the dependent variable, the speed depends on the distance from the observer in this case. Okay? And this is spectra. And these little lines here are very important, and you need to be able to analyse those. So we'll talk about that now. Okay. Now, you don't need to take notes particularly on this, although you do need to take note of that bottom point there. Electromagnetic spectra, range of wavelengths and frequencies over which EM radiation extends. You've got this in your notes already. I always use the same slides, and I just bring them through so that it's more, it gives you a better, it's better in terms of revision. Now, all of this EM radiation from radio all the way through to gamma rays is emitted in photons. It's both a wavelength, sure, and also we think of it, we model it in terms of photons, these individual, effectively massless particles, if you like. Now, you won't be tested on what photons are, but you just need to be able to conceptualise them. You've already looked at light speed, and I already emphasised before that the sun is emitting photons or wavelengths right through there. Remember the radio signal that we listen to from the sun? We can of course see visible light easily, just look outside the window. And of course you know UV is always out there, and X-ray and gamma rays. So the sun is emitting all of those, and that's important. Okay? So any questions about that there? Now that's something we've looked at before, and they're all of course moving at light speed. Now I mentioned this point the other day, and this is somewhat new. The blue text is not examinable in a real sense, but it does help you understand things. Okay? This is the periodic table, but we don't have hydrogen and helium, but we've got lithium, beryllium, boron, carbonate. So you can see that we've got our group 1, 2, 3, 4, 5, 6, 7. None of the noble gases, they're not needed. And the trend that you can see is, as you go across the periodic table, the elements in each group get smaller. And that is important. Okay? So, long story short, any of those two, are the atoms of any of those two elements the same size? No. Okay, each element has a unique size, and that's important because that particular characteristic is tied into spectra. Different elements have different diameters, and therefore the difference between the shells is different. Like sodium has, let's see, it's got a, sodium is, it's got a K and an L shell. Now, so the distance between the K and the L shell for that particular element is different to the K and the L shell distance here or anywhere else. And I've got another diagram to explain that. Okay? So, and when we get onto year 10 chemistry, you'll see that diagram again. Okay? Because that explains why some elements react more than others. You've just, well, may as well cover that. You've done ionic bonding, yes? When atoms donate electrons or accept electrons, yes? Now, these are group 1. They all donate a single electron, as group 1 elements will, because group 1 metals will. Now, did you watch the video of these being dropped in water? Well, this is a bubbly, they all give off hydrogen if dropped in water. This one bubbles pretty violently, very violently, cataclysmically violently. Really, you don't want to be in the same room. That can't be, cesium is ridiculously dangerous, and then francium, which is further down, is so volatile it's not really found in nature, because as soon as it touches atmosphere or water, it just goes. Okay, and but they have the same reaction, but it becomes more violent as you go down. And why is that? Because the single, this one will donate 1 electron. How far is that electron from the protons in the nucleus? Well, we'll just say in centimetres, about 2 centimetres. Okay? Is this single electron closer to the nucleus or farther away? Further away. Same reaction, but more violent, because this electron isn't really strongly bound here, and the same pattern goes on. The electron, as it gets further away, is less strongly bound. You'll need that for chemistry when we come down to chemistry again. Now, this is the picture I changed. Okay? If an electron in an atom gets hit with a photon with exactly the right energy, not close to it, but exactly the right amount, the electron will become excited, and it might jump up 1 or more levels. It's not going to jump up, down, up, down, up, down. It gets hit once. If it gets hit with the right amount of energy, it'll jump up a level. If it gets hit with a different but right amount of energy, it'll jump up 2 levels. And then when it falls down, it emits further energy. Now, the energy, say that was the electron there, it gets hit and jumps up 1 level and then falls back down and emits energy of a different sort. This is visible. This might be UV coming in. Okay? UV energy comes in. So this is literally emitting a little ray of visible light. Detectable visible light. Coloured visible light. Red, orange, yellow, blue, green, indigo, violet. I'm not sure if at that wavelength, at that length, what the colour is, but it's visible light. Now that's for hydrogen. This is helium having the same kind of reaction. The electron was there. It gets hit with exactly the right amount of energy, but a different right amount of energy. Which of these is bigger, hydrogen or helium, in terms of size?
Hydrogen.
Actually, it's hydrogen. I know that because I made it that way. It just doesn't appear that way. It's easier when they're up the top. But if you look close, relative to the text, you'll see that the helium is actually smaller. Okay? And so this distance is different. The difference between the K and the L shells is different. And so the height that the electron jumps is less, and the height that the electron falls is less. So the energy that it emits when it does that is less and different, but still visible. You understand? So that is just a simple example. One electron in the case of hydrogen, one electron in the case of helium. The difference in size means a different jump and a different colour being given off. Now, let's have a look why this is significant. Okay, here is some visible light. This is all 7 colours. So we'll say Roy-G-Biv there. Red, orange, yellow, green, blue, indigo, violet. There's Roy-G-Biv, visible light coming in. Here is a cloud of hydrogen atoms. Now, some of them, not all of them are going to act the same unless they get hit by energy of the same sort. So this one here, getting hit by the right energy, it'll jump up one level, it'll jump down level. But this one here, hit with a different but correct right amount of energy, might jump 2 shells and therefore falls 2 shells, so gives off a different coloured wavelength. Okay? Now what's actually happening here is a little bit of the opposite of what I've just said. This is visible light coming in, and what's being given off might be infrared light or something like that, not visible light. These shadows, these gaps here are, remember, this is all possible wavelengths for visible light, and some of that visible light is being absorbed by these electrons. And so you get these lines here. This is the pattern, the spectra, that's unique for hydrogen. Okay, remember hydrogen has a unique size. The electrons can only jump so high. And so this is all possibilities for hydrogen electrons jumping when energized. And so the visible light, if there was no hydrogen there, we would have on the wall here just red, orange, yellow, blue, green, indigo, violet. We'd have our spectra, yes? But because some of that visible light has been absorbed, we get these gaps. And those gaps are the fingerprint, if you like, for hydrogen. Only hydrogen has that pattern, because only hydrogen electrons will jump in this way. Let's look at the flip side of that. Same situation, but this is UV light coming in. UV light coming in, electrons in a hydrogen gas cloud, absorbing some of the UV light wavelengths and jumping up and down, and then giving off coloured light when they fall back down. And so in a black background, because is UV light visible in terms of our eyes, for example? It isn't. But what these guys are doing as they jump up one or more shells and jump back down, they're giving off coloured light of certain frequencies. Notice that the spectra, if we flick back and forth, are identical. One, the other, one, the other. Yeah? The first one is called an absorption spectrum because some of the visible light is absorbed by these electrons in the gas cloud, and we get these shadows here. Okay? If you shine white light through gas, e.g. hydrogen, the electrons in the gas will absorb certain wavelengths of the white light, and they get excited, and they jump up and they jump down, and you get these shadows forming, okay, which are unique for hydrogen. Okay, can I change?
Yes.
Yep. And what we have here is the spectra unique for hydrogen, but this is UV light coming in and coloured light being emitted. Now, the good news is this. Those slides that we've just looked at are complex, but not examinable. You won't be asked to explain why spectra form. So you don't, in terms of atomic radii and jumping up and down levels, you won't have a question on that. I guarantee that. You just need to know that because all of the elements are unique, they all have unique spectra. It's like a fingerprint. Okay? Now, why is this useful, or how is this useful? Well, let's have a look if we had the example of, I think I told you this last time, if we had a star fusing hydrogen over here and emitting energy, including visible light, and what would this atmosphere consist of? And you go, well, because this atmosphere is absorbing the visible light, this atmosphere is mainly hydrogen, and because it's absorbing visible light emitted by the core, fusion in the core, you get these lines forming here. So you can actually deduce that that particular star is, has mainly a hydrogen atmosphere. Or another cool thing you can do is you can determine the atmosphere of a planet, a far distant planet. If white light is shining through that atmosphere, you can find out what is in that atmosphere based upon the spectra, because the atmosphere of that planet will absorb certain wavelengths depending upon what is in that atmosphere. So one of the ways they think they might be able to detect life on a distant planet is using the spectra that you can gain from that planet, from the atmosphere in that planet, and you look for gases that shouldn't occur normally, like methane. Methane is produced biologically, but it doesn't occur in large amounts naturally. It just doesn't. Okay? So you'd actually be able to discover life on a far distant planet without sending robotic craft or anything at all, just based upon spectra. Now, there we go. Because each element is different with different radii, we decided that each element emits certain wavelengths of light that form a unique pattern. That really is examinable. That one there is examinable. And I might just to emphasise that, I'll insert slide numbers. Where are they? View, file, insert. Sure, I'm sure it's there. Slide numbers, there you go. So if you want to make a particular note, slide 12, that particular core idea is examinable. So here's hydrogen's unique spectra. Here's sodium. Here's helium. Notice hydrogen and helium are pretty similar, but they get very distinct spectra. Here's neon. Here's mercury. Yes?
So we have to tell the difference between these?
No.
Okay.
We wouldn't be that mean to you. Although I did see a question once where it said, here's a spectra, and what gas is present in the atmosphere, but you had references, yeah? But the spectra was a combination of these, of two of them. So, for example, if we combine neon and hydrogen, you'd have all of those, that one, and all of those. And you'd probably be able to work it out, yeah? So, it's not as neat as this. You don't just get from a planet, a distant planet, one spectra. They'll all be bunched together, but you can work it out. Use software to work it out. Now, this is where rubber meets road. Red shift and blue shift. This is taken directly from an exam paper or from a test paper, I forget which. This is a spectra. I don't even know which gas this is. Okay, which element this is. This is unshifted. Now, this is the same pattern, but do you see how it's shifted slightly to the right? This is the blue end. See, look, single, double, triple. Single, double, triple. 1, 1, 2, 2. It's the same pattern, but it's being shifted to the right. Why is it blue shifting? Because whatever is emitting this light is approaching me. Remember, blue shift, it's coming towards you. Red shift, it's moving away from you. So this is on Earth. We'll just say this is lithium. I'm just going to make that up. We'll just pretend this is lithium. So in a lab on Earth, if I shine white light through lithium, I get this spectrum. If I look to a distant galaxy, for the lithium signature and I see this, I know the distant galaxy is moving away from me. Why do I know the distant galaxy is moving away from me?
Because it's redshifting.
Because it's redshifting. The same pattern that we see on Earth, but it's pushed that way. And the faster and you could get asked this, you might get two redshifted patterns, and they ask you which one is moving faster. The more it redshifts, the faster it goes. Remember how we said with Hubble's law that the distant galaxies are moving faster? They're looking for the same element. In every galaxy, they're looking for the same element or elements, the same spectra, and they're seeing how far they are shifted. So if this was really moving fast, all of these spectral lines would be really pushed towards that end, but you'd still have the same pattern. Any questions? So that is how you can determine, using spectra, if something is moving towards you or away from you, and how fast it's moving. By how much it's shifted, how much a spectral pattern has shifted. And that pretty much precisely is what you would expect to see on any kind of assessment. That they give you one of those. Okay. Any questions? Now we'll have an opportunity to practice that a little bit, but that is why spectra is important. Now I think that's just about done. Oh yeah, that's it. That's just of interest. And I think I've already shown you that before. Okay. A few quotes from Stephen Hawking, and that particular little thing there about the Hubble Space Telescope's discovery of distant galaxies.